Hello there, this is Miss Nakayama, and today's lesson is 9.5 Parametric Equations. This is the last lesson in our study of conic sections. So to start off with, parametric equations give us a good way of solving applied problems. So I kind of want to point out to something to you. If I had a real life problem, I'm standing on a rooftop and I throw the ball will go up and then it'll come back down because we have gravity. We have our x-axis, we have our y-axis, and if x represented the time in seconds after I threw the ball and y being the height of the ball, then I could simply write an equation, and very simple purposes for this video, and have it be negative 16x squared plus 35. And if x represents the seconds, then we know that at 0 seconds, this is 35 feet. That's where the ball is. And perhaps at 2 seconds, it's up here at its highest. But x in time represents the height of the ball. Well, if we introduce another variable, which we call the parameter, then if I pick a point on this graph, excuse me, that variable time, I could write each equation x in terms of t and y in terms of t, and that would give me a set of parametric equations such that any time that I threw the ball, I could find its horizontal distance and its vertical distance. And that's the main thing for parametric equations of why we have them. It gives us a lot of more information about real life problems. So what we're going to do in this video is we're going to use points to plot the graph described by parametric equations. We're going to eliminate the parameter, we're going to find parametric equations, and we're going to solve applied problems using parametric equations. So, as I just mentioned to you, if I have t on some interval, then I can have x equal to something in terms of t and y equal to something in terms of t. X and y would be my parametric equations. T is that parameter. Okay? Here are the steps to graphing with parametric equations, but I'm just going to show you. You can copy those down if you want to, but I think it's better to go ahead and get started. Graph the plane curve defined by the parametric equations below. So if you remember when you first learned how to graph, you didn't know how to graph anything, then the first thing you did was actually make a t-chart. And so my t-chart, a little more elaborate because I got more variables. I'm going to start off choosing numbers to plug in for t. And I'm going to choose those numbers, and then I'm going to plug it into the x equation to get an x value, the y equation to get a y value, and that's going to give me an ordered pair. So if I start off with, you're like, where, y'all are used to saying, I'm just going to do negative 1, 0, 1. That's fine and dandy, but really what you have to pay attention to is the problem. And it tells you that t is in between negative 2 and 2 inclusive. So that means I'm going to choose the numbers negative 2 to 2. And you can pick whatever numbers you want. Integers are the easiest ones between there, but you can choose whichever ones you want. And really, you only need to plot enough to be able to tell what the graph is going to look like. But if I plug negative 2 into x, then I'm going to get x equal to 5. If I plug it into y, I'm going to find y equals negative 6. And so I'm going to have the point 5, negative 6 on my graph. So I would go 1, 2, 3, 4, 5, and then down 6. And there's 5, negative 6. If I plug in negative 1, I'm going to get 2 for x and negative 3 for y. So I'm going to have the point 2, negative 3. If I plug in 0, I'm going to get 1 for x and 0 for y, giving me the point 1, 0 on my graph. If I plug in positive 1, I'm going to get 2, 3, giving me the point 2, 3 on my graph. And then if I plug in positive 2, I'm going to get 5, positive 6, which is going to give me the point 5, 6 on my graph. And I do need to connect them, which, oh well, don't really do very well in this, but you got the right idea. Oh my goodness, it's pitiful. But anyway, so here's my graph. And one of the things that you got to remember when you do these is that you have to show direction. And we show direction by using arrows on the graph. So whenever you see a set of parametric equations, you will actually see arrows on them. And what you've got to go back to is this interval and say, I started at -2. And -2 gave me the point 5, -6, which was down here. And so this is where I start, and I go this way on my graph. So you will see arrows. Usually when we draw them by hand, we draw more than one. But that gives us an idea of what direction, the path of whatever it is your parametric equations are trying to model. Okay? So next we need to be able to eliminate the parameter. And when we do that, you have to pay attention to the domain when you do so and see if there's any kind of restriction in the domain of your parametric equations. So look at this, our second one, finding and graphing a rectangular equation. And the directions say sketch the plane curve represented by the parametric equations by eliminating the parameter. Now, we can go, if you wanted to sketch this graph, you could go make a t-chart just like we did before. However, it's not always easiest to do that. That's why they said eliminate the parameter. Sketch it by eliminating the parameter. So we're going to go eliminate the parameter. Hopefully you notice there's some trig functions in there. So when we do, the first thing I want to do is go isolate those trig functions. So when I do x equals 6 times the cosine of t, I'm going to divide both sides by 6. So that's going to give me x over 6 equals cosine of t. And then I'm going to go to the y equation, and I'm going to divide both sides by 4. So y over 4 equals the sine of t. And then the technique that you want to use to continue to eliminate the parameter is to square both sides of the equations. So when I do that, on the left side of my x, I get x squared over 36 equals cosine squared t. And then I get y squared over 16 equals the sine squared of t. Then you remember from our chapter 5, your favorite chapter, that the cosine squared plus the sine squared is equal to 1. So if I just make this substitution for cosine squared and this for sine squared, then you'll see that I'm going to get x squared over 36 plus y squared over 16 is equal to 1. So you should know from previous sections that this has a center at 0, 0. And that means that this is my center. And I'm going to go left and right 6. I went right, 1, 2, 3, 4, 5, 6 to the left. And then I'm going to go up and down 4. 1, 2, 3, 4. 1, 2, 3, 4. And you should know that it does look like an ellipse. So I'm going to try to make it look like an ellipse. Something like that. Okay? But as I said, we always have to draw arrows on it and figure out which way it goes. So I'm going to go back up here. And it said that t is in between pi and 2 pi. Well, if you remember your unit circle, pi is over here and 2 pi is here. And if I go from pi to 2 pi, that means I only need the bottom half of this ellipse. And that is my graph. And the direction that I went was this. So this is what my arrows are going to do. And if you want, you could go back to what we did on the previous problem, and that is to make a t-chart to figure out your direction. Okay, so if I chose, I would choose pi, and then I would choose 3 pi over 2. And when you plug in for x, you're going to get x is equal to -6, y is 0, which is this point right here on my graph. And when I go to 3 pi over 2, I'm going to get x equal to 0 and y equal to -4, which is this point on my graph. So you're going to get the same thing either way that you do it. Now, not every set of parametric equation has trig functions in it. So here's another one that you might see. X equals t minus 3, y equals t squared plus 1. T is in between negative infinity and positive infinity, and then we need to eliminate the parameter. What is the parameter? Well, our parameter is going to be always the letter t. So you can pick either equation, it does not matter, and solve it for t. Well, I hope you realize this is the easier one to solve for t, because all I have to do is add 3 to both sides of the equation. And after I get t equal to x plus 3, then I'm going to go plug it into the other equation. And that's all you have to do. Don't make it any harder than that. So y equals x plus 3 quantity squared plus 1. Okay, now we're going to go backwards, and that is, given a function, we're going to go write parametric equations. This is the simplest way to start. The simplest way to start, okay, example 4, find a set of parametric equations for the parabola whose equation is y equals x squared minus 25. So the simplest way to start is say x equals t, and if x equals t, then I'm just going to plug t into that second equation, and I'm going to get y equals t squared minus 25. Simple enough. But you're not limited to that. You could also write x equal to t minus 1. And if x was equal to t minus 1, then y would be t minus 1 quantity squared minus 25. So, as one of my students put it this year, there are an infinite set of parametric equations that I could use to actually write that would model this same parabola, that same equation. Okay, last problem we have to talk about is applications. All right, it tells us the path of a projectile that is launched 8 feet above ground with initial velocity of v sub 0 feet per second at an angle theta with the horizontal is given by the parametric equation shown below, where t is the time in seconds after the projectile was launched. So this is x equals something and y equals something. The figure shown below, down here, shows the path of a baseball after being hit. The ball was hit with an initial velocity of 100 feet per second. That's v sub 0. That's my initial velocity. At an angle of 50 degrees to the horizontal. That's my theta. The ball was hit at a height of 3 feet off the ground. That's my h. So, answer questions A through D. So, couldn't all fit on one slide. So, we have lots of them. Find the parametric equations that describe the position of the ball as a function of time. So which of these, 1, 2, or 3, is going to model this particular function? Okay, well, I have to have a minus 16t squared, y'all, so it can't be this one. And then the only difference between these two is, was the angle 50 degrees or was it 140 degrees? Well, it was 50 degrees, so that means that this middle set right here are the equations that model this function. Okay, so now we're going to actually describe the ball's position after 1, 2, and 3 seconds. What is the position of the ball after 1 second? So I'm going to go back, make my little t-chart, and I'm going to plug in 1, 2, and 3 into my x equation that we just figured out and my y equation. So after 1 second, x is going to be 90, rounded to the nearest tenth, and y is going to be 94.2. So that's my first ordered pair. When I plug in 2 for t, I'm going to have 180 and then 153.5. And if I plug in 3 for t, I'm going to get 270 and then 180.7. And that's my third one. Okay, so again, that is allowing us to know the ball's position as a function of time, horizontally and vertically. All right, last but not least, they want to know how long is the ball in flight. You know how I need to go for this. Hold on. So, how long is the ball in flight? Well, here's my picture down here, and the ball is in flight the whole time this red curve. It's not in flight when it hits the ground, which means that the y coordinate is 0. So I'm going to take that 0 and set it equal to that, plug it in for y to that equation. And if you were in class, I showed you how you could use the black calculator to solve that. If you need help with that, let me know. I'll be happy to help you. But otherwise, you would take that 140 sine of 50t. I would go ahead and do the 140 sine of 50 and write it as a decimal. And now I have a quadratic, okay? And I'm going to use the quadratic formula. It's not going to factor. I'm going to use the quadratic formula to solve it. So t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And when you plug that in your calculator, you're going to get negative 0.03 and 6.73. Okay, when you do this, okay, notice on our picture, so it's way over here. That means this thing comes past the y-axis. That's the negative 0.03. And then over here, it is at 6.73. So 6.73 seconds, or 6.7, because we're going to the nearest tenth, is how long the ball was in flight. What is the total horizontal distance the ball travels before it lands? That's the x equation. So I'm going to plug in 6.7. In this case, probably should have plugged in 6.73, but I didn't, so I got 602.9 feet. And that is all we have, two parametric equations. Thank you so much for watching, and y'all have a great day.